start recording. So we're jumping into chapter 2 on alternating current. There's actually 2 chapters on just dedicated to alternating current. This first chapter is going to focus on what's known as a time domain analysis, meaning the things we're going to look at is basically whatever's on the horizontal axis, we're going to look at it in terms of time. And usually it's like voltage in terms of time, right? And then so alternating current is up and down, up and down, up and down. It's alternating up and down, right? Usually it's a little bit more complicated than that, but we're going to start off with a very simple case. And the reason that alternating current is very important is because all of our electrical system is on alternating current, right? The power generator from a fusion reactor, for example, spins a turbine, and as that turbine spins, right, it drives a generator inside a magnetic field, and as that magnetic field turns, it basically creates an EMF that's going up and down, up and down, up and down. Okay, and it just makes sense for us to use that as the electrical system versus converting it to something else. Okay, and we'll talk about actually there's an argument back in the 1800s when Edison and Tesla was trying to figure out which one is actually a better electrical grid, DC power versus AC power, and eventually, of course, Tesla won, but he got banished to like Colorado or something like that anyway. But that's a long history story. But and Edison is just a much better business person compared to Tesla. Tesla is just not as good in business. And that's why he kind of got ousted by a lot of the scientific community in the 1800s when he was promoting that AC power is actually the best way to transfer energy from one side of the country to another, for example. Okay, so this is when when I was taking this class, this was my understanding of AC circuit, right? It's like power, stuff like that. But actually, AC circuit is much more important than that. Okay. All of your information is actually sent back and forth via AC signals. It's not just a power delivery system, it's an information delivery system. Okay, so for example, my phone, right, it sends a little signal up to the cell tower or the Wi-Fi router here. All of those signals are actually waves that are alternating up and down, up and down, up and down, and hence it's actually can be detected, measured, produced by alternating circuit currents, alternating circuits, because they are alternating voltages. Okay, so all data transmission actually happen on alternating current circuits. Okay, and this is this is these 2 guys back in the 1800s when they were having this thing called the current war, right? And if those of you who are interested in why DC power is actually not a very good, well, how many of you guys, well, what do you guys think? Why is DC not a good way to transfer power back and forth? Anyone know that? Or have a guess? Yeah, Alan?
DC would have to convert AC to DC.
Right. The first thing you do, right, if you had let's say you have a windmill, right? Right. A windmill also produces AC in AC, right? And you can have a little box here, right, that converts it to basically like a constant DC voltage, right? That works, right? But what happens when you send this DC voltage over a long distance? It loses its voltage, right? So instead of when you're up here, right, depending on which house where you are, how close you are to the generator, right, instead of getting 120 volts, right, you might get 110. The guy further away will be 100, right, and then the person further away will be 90, right? Everybody gets a slightly different voltage, right, which is not a good thing. Okay, but you can make the same argument with AC though, also, right? As the AC signal goes further and further and further, it also diminishes, right? The cool thing about AC is that you have these things called transformers. So the way we actually built our electrical grid is basically at the generator, you're basically producing about 100 kilovolts, okay, which is not what we use. And then that power gets sent to like a city, right? And then the city will distribute that amongst all of its streets to the street level. at about 20 kilovolts, okay? And then that 20 kilovolts gets converted to this 120 volts that we use, okay? So basically, the distance that you actually have the 120 volts is about, how long a street is, okay? So maybe the person right next to the transformer gets 125, right? But then the person at the end of the street gets 115, but that's still okay. Your electronics have that tolerance so that it could deal with this, plus or minus 5% thing, right? Just like our resistors, right? Our resistor is actually plus or minus 5%, right? So all of these electrical systems are actually pretty good, pretty robust, up to about 10% difference. So that's why, when you well, this is not a good example. When you have like a device like a multimeter, right? Even though it's designed for to run on a 9-volt battery, right? As the battery drains, it actually goes below 9 volt. It's like 8.5, 8.4. It still works up down to maybe like 8 volts. Okay, so there's a tolerance on how small this voltage is. But right, if you're dropping this over a length of the street, maybe it's 10%. But if taking, I don't know where we generate our power from, like Don Pedro or something like that, right? Right? You're talking about like tens of miles, right? And that's going to drop your voltage by maybe even 50% by the time it gets here. So you don't want that. Okay, that's a little bit about electrical grids. But in our class, we're going to focus on small voltage stuff, meaning mostly dealing with signal type of AC circuits, okay? We're going to be using AC circuits to measure data signals, okay? How to differentiate different frequencies of signals. So, how do you figure out, if this is 900 megahertz, 800 megahertz, whatever megahertz you want, okay? And also filtering out these signals using the frequencies, okay? So actually don't know the frequency of cell phones, but my Wi-Fi, right, is 2.4 gigahertz. Does anyone knows another frequency that the Wi-Fi router actually uses? 5 gigahertz, right? So you can actually have, it's the same device using two different frequencies, and the way you pick one versus the other is that inside here there's a little circuit that you can determine. Oh, I'm going to pick out the 2.4 gigahertz signal and ignore the 5 gigahertz signal. Okay, and that's how you can actually use different frequencies in order to send information in parallel to each other so that one device doesn't bother another. Okay, okay. We're gonna figure out how to amplify these signals. Okay, this is when we get to operational amplifiers. Okay, and how to transmit this data and how to receive it on the other end. Okay, how do you send and receive data? And basically, this is the first half of the class. Not this class, but the whole course. Like the next up to lab 7, this is what we lab 7. You'll be basically building a transmitter and receiver, okay, that can send signal in through the air. It could send signal through the air, but we're doing it through a fiber optic instead to make it a little bit easier because you guys are going to be building them right next to each other. Okay, so back to general physics, right? AC signal, right? It's a cosine wave. It goes up and down, right? Right, and it's described by some, voltage as a function of time, so it changes, right? That's why it's alternating, okay? It has some amplitude. Remember, this is like the how high it goes, how low it goes, right? This is the amplitude of the wave. Does anyone remember what omega is? The what? The angular frequency, right, of the wave, okay? And time is the dependent variable, right? It depends on, oh, this is the independent variable. I always get these mixed up, right? Because v is a function of time, independent variable, okay? At some point, I'll be able to spell independent, okay? This is voltage, right? Okay. Notice that this is signified with a lowercase v, right? Remember in electrical, physics or electricity or electrical engineering, the lowercase means a time-varying variable, okay? Where a capital V is a constant, okay? Right? So it goes up and down and, has some wavelengths, right? Because this is actually going with respect to time, right? So this is with time. So typically, so this wave is only a single frequency, right? Typically, you're actually dealing with multiple frequencies, okay? And hopefully, if you remember from general physics, if you have like two signal that has multiple frequencies together, they end up kind of like interfering with each other, and then you have this weird shape, right? That you can't really differentiate yet, okay? And we're gonna figure out how to do that in this class, actually, with electronics, okay? As opposed to just doing it by math, okay? So let's go back to our previous discussion on basically calculating the power from a DC circuit. Let's go roll back to last Wednesday, right? Last Wednesday, I told you that while the power off a DC circuit is just the current times the voltage across that resistor or that device that you have, right? Right? Using Ohm's law, you can change this to other stuff, right? And since alternating the current, right, the voltage is not constant, right? We have to find a different version of it, right? The power through a resistor on an AC circuit, right? I'm going to draw AC circuit light, so that's my AC source, right? Whatever that is, right? Could be the wall, it could be my Wi-Fi signal, whatever that is. There isn't actually a wire here, okay? And we're driving this signal through a resistor, okay? The power that's being dissipated by this, right? It's the same thing, right? It's the current going through my little resistor, right? But now it's a current that depends on time, right? Because when the voltage is positive, right, it's going to drive current this way. When the voltage goes negative, it's going to drive current the other way, right? It's just going sloshing these electrons up and down, up and down, up and down, okay? And you multiply that by the voltage, you get the power once again, okay? We don't have to really worry about the stuff on the right, okay? Actually, you do. Yeah, let's just convert this to the using Ohm's law, you can change this to basically I squared times R, just like up here, right? So because V equals IR in this case, right? So lowercase v equals to lowercase I times, well, there's no lowercase r, right? Because r is a constant. Once you plug your resistor in, it doesn't change, right? Okay. Okay. You plug this in here, then you get I squared times R will give you the power also, okay? Okay. Since the voltage, right, is a function that depends on time, equals V naught times cosine of omega t, right? Let's just pick one frequency for now, okay? The current is going to be proportional to that, right? The current is going to be some amplitude of the current, whatever that number is to be determined, right? Times cosine omega t also, right? Because voltage and current are proportional to each other in a resistor, right? Just like what you just measured right now in part B. Okay, so you can plug that in here, right? When you plug that into here, you get, I'm using slightly different notation from different books, but you can just change that, okay? Sorry about that. Okay, you get basically the amplitude of the current square, because you're squaring everything here, right? The R stays the same, but then you get cosine square of omega t, right? Because you have the current square here, right? Okay. Well, now you got a cosine square function, and what the heck is that, right? Okay. So if you remember your trigonometry from years and, well, for me, like tens of years ago, right? There's a trig identity between cosine square, right, that changes it to 1/2 plus 1 times cosine 2 of omega t, okay? Right, so this is stuff you have to remember, and what I'm going to talk about in the next section just is going to say, okay, let's not remember any stuff, so just forget about it, okay? And then we're going to see why it's useful to use these things called complex numbers to deal with this. But what's really neat here, right, when you simplify this, when you multiply this out, right, you have a constant term, and then you have a cosine 2 times omega t term, okay? Okay, so you have when you calculate power, you get a constant, and then you get twice the frequency, okay? So if we're looking at this little sketch here, right, this is still from the General Physics 2 textbook, right? If your current is going up and down like this, okay, the power that's going through that resistor is going to have a constant shift up, right? Because the constant basically just gives you a shift up in the function, right? If that constant is 5, I'm going to oscillate around 5 instead of oscillating around 0, right? If that number is 20, I'm going to oscillate around 20 as opposed to 5, right? And that oscillation has an amplitude of 1/2 I square R, right? I'm just ignoring the I sub R thing, but when I talk about current on a resistor, right, I'm always talking about the same current, okay? So it has this amplitude here, okay? And it's gonna oscillate at twice the frequency, okay? So you notice that, this goes up and down about this much time, right? If you bring it down here, it goes up and down, so it does it twice in the same amount of time, right? It's the frequency doubling, okay? And that's because of this trig identity that you have to remember, right? Right? And that's the annoying thing about trig identities, because there's like 5,000 of them or something like that, and you have to memorize all of them to do all this math, right? Okay. Before we go on to figuring out how not to deal with trig identities anymore, we can also rewrite this into something called a root mean square average. Okay, notice what's up here, right? You ended up with a factor of 1/2 in front of all of this, right? Okay, what you can do, and what we really do, is that we define something to be um, whatever the root mean, whatever the current amplitude is, right? We just divide that by square root of 2, and therefore when you square it, because all this stuff it gets squared, right? It just knocks out all of these 1/2 terms in front of the power, and therefore you can use the same equation. So if you're using DC current, power through a resistor is the resistance, the current through the resistance times the voltage across that resistor, right? Okay, but now if you change to AC, the power through that resistance, so through that resistor, you either have to write this 1/2 all the time, right? Or if you just replace this with IRMS all the time, okay, which is equal to whatever the original is divided by square root of 2, right? If you square this, right, this gets squared. This goes to 1/2, right? Oops, sorry, I did this wrong. V squared times R. I knew that was a resistor somewhere, right? When you square this, right, what ends up happening is that basically you have the same looking formula between the two, right? So it's some current square times R, some current square times R, no matter if you're dealing with AC or DC, okay? And that way you don't have to memorize two different formulas. Is there a factor of 1/2 or not a factor of 1/2, right? These are the really annoying things you don't want to remember, right? But if you're dealing with RMS, meaning you basically knock the amplitude down by square root of 2, you can use the same equation for both, okay? And that's what people decide to do, okay? Right? So you always have to, no matter when it's AC, you knock the amplitude down by square root of 2, okay? In fact, I think I talked about this with you guys already, right? The voltage up here, right? It says 120 volts. The amplitude is actually 170, right? It's the RMS voltage that's 120, right? It's 170 divided by square root of 2. That gives you 120, okay? All right. So that's sort of like the level that when we talked about all this AC stuff when we were doing it last semester or whenever you took General Physics 2, right? Dealing with these sine cosine functions, okay? I'm gonna do this the book does a little segue into complex numbers so that we don't have to deal with this trig stuff anymore, okay? So those of you who are in math physics will see this again in a few weeks when you guys cover complex numbers. But I'm going to give you guys like a very, very simple, like a little baby complex number stuff, okay? Right? So a complex number, right, has a real component and an imaginary component, okay? Does anyone remember what imaginary number is? Anyone remember? What's an example of imaginary number?
Square root of 2,
So what's another example?
square root of -2.
2, okay? So, yeah, square root of -2, that's actually a imaginary number, right? What you can do right, is to rewrite this so that you can factor out the square root of -1 times the square root of square root of 2, right? I'm going to define this as, okay, in your math class, they define it as I. In this class, we're going to define that as J. Okay, why don't we want to use I, lowercase I? Because we use current all the time, right? So that's why we use the letter J. It's a little bit annoying that it's different between them, but, you know, yeah, it'll be more confusing when you say I equals to, 3I or something like that, right? That doesn't make any sense, right? Okay, so this is the imaginary number. Okay, what you can do is you can combine this with a real number, let's say, and typically they use the letter Z for it, where let's say you have a number, 3 plus J square root of 2. Okay, so what the heck does that mean? Okay, so this is the real part of the complex number. This is the imaginary part. Okay, okay, and it's just a mathematical tool, so then we can multiply and divide and differentiate and integrate trig functions very easily. And we're going to see how where this magic comes, where this really cool thing comes from once we just take this as a given that these are the definition of these things. Okay. Okay. So what you want to do when you think about imaginary number is that you have a plane, right? Instead of thinking about x versus y, you want to think about the vertical axis as the imaginary axis, and then the horizontal as the real axis. Okay. So in general, right, you can write a imaginary number as just a plus jb, right? Okay. So if a if a is a positive number and b is a positive number in this case, right, they're both positive, then you have something that's pointed this way, right? But, right, if a is a negative number, right, let's say a2, b2, right? A2 is a negative number, b2 is a positive number, you have something pointed this way, and then, and so on like that. It's just kind of like xy plane, but they're not real. So one axis is not real, right? One of them is imaginary, okay? Right? So if you're interested in the real part, the notation that people do is that RE, right, of Z, in this case, is just going to be A, right? You're just ignoring the imaginary part completely, okay? If you're interested in the imaginary part, you put an IM, right? And that's going to be equal to what in this case? And for this number? B? What about the J? I'm just being mean. Yeah, it's just B, right? You drop the J, okay? Because by saying this, the imaginary part, you assume that anything on your complex number that has to multiply by J, that's the imaginary part, okay? Okay. Now we go a little further. I don't know if have you guys seen this? Where if I want to write this function e to the x is 1 plus x squared 2 factorial. And people may not even know what a factorial is, okay? But are people seeing the pattern here? This is easy for me to remember. What's the next one? X to what power? 5, right? And then what should I write on the bottom? 5 exclamation mark, okay? Okay. This little factorial thing is just a shorthand for writing 5 times 4 times 3 times 2 times 1, okay? This is called a factorial, okay? Anyone who plays anyone who plays poker would know this number, know this math, but I guess a lot of people don't play poker anymore. Anyway, so that's the definition. That's how you actually can calculate numerically what an exponential function is. This keeps going into infinity, um, but what you can do, right? Instead of thinking about it in terms of x, what if I think about this in terms of j times x? The imaginary square root of 1, right, times x, right? So the same formula applies, right? Instead of writing x, I have to write j everywhere in front of the x, right? I'm just writing j's everywhere, okay? Why am I doing this, okay? Well, 1 is 1. J times x, that's like a complex number thing, right? But what's j squared times x squared? Right, negative x squared. It goes down here. Okay? J to the third times x is what? So j squared equals to negative 1, right? J times, what's j times j squared then? Negative, what? Negative j, right? Because there's one little factor of j left, okay? So this j to the third, right, is actually j times x to the third, right? Oops. Okay, don't worry, no one got hurt. You see where these terms are showing up from one place to another? I'm just doing really boring algebra stuff, okay? And then hopefully it'll turn into something useful, right? Okay. So this number 1 goes here, this j goes here, right? J to the fourth, what do you think that's going to be? Is that going to be a positive term or a negative term? It's positive, right? Because you have two negative ones multiplied by each other, right? So that's going to turn it into a positive term. So that goes here. Okay. So what I'm doing is I'm actually sorting it so that all the stuff that has no j's in front of it goes in this little piece. All the stuff that has j's in it goes in this little piece. Okay. So this is going to be j to the fourth times j, right? So j to the fourth is just 1, so that's just going to be a positive j, right, where this factor goes in, right? Everyone seeing that step where I'm just kind of separating e to the jx into stuff that has no j's in front of it, and those that does, right? So now I have the real part and the imaginary part, right, of my exponential function. Okay. One more thing. Okay, this is one thing you can look up, or you get used to it, right? When you have just odd powers of x that's alternating plus minus, sorry, minus plus, next one should actually be minus, actually. Minus plus minus plus minus plus is actually cosine. Okay? If you don't know this, that's okay. You're going to learn it in like a couple of weeks in math physics. Or do they teach you this in like Calc 2 or 3 when you do series? Any, the, I'm sorry? Calc 2? Yeah. They talk about series. Yeah, but you probably forgot about it, which is fine. Right? Right? The x's with odd number of power and alternating minus plus minus plus minus plus, that turns into a sine function. Okay? Okay? So the real part of this exponential is cosine of x. The imaginary part is just sine of x, which is really nice. Because remember what we had to deal with when we did cosine? When we do like cosine square, we have to remember, oh, go to internet, look up this trig function stuff, right? Well, let's see how that happens now. Okay, right? If I multiply two, right, two complex numbers together, right? Let's say z1 is equal to e to the, oops, let's do r1 e to the j phi 1. Okay, it's just me making up some variables. Okay, just pretend this is x, right? It's okay, right? Okay, and then z2 as r2 e to the j phi 2. Okay, it's just numbering things. Okay, if you don't like the phi, just replace them with x1, x2. Okay, it's fine. It does the same thing. Okay, well, if I want to multiply these two numbers together, right? Z1 times Z2, right? If I multiply these two numbers together, right? These two terms, these two factors actually just collect in front of it, right? When I multiply e to the j phi 1 times e to the j phi 2, what should I do with the exponentials? What's e to the 3 times e to the 5? What does that equal to? E to the 8, right? Because exponential, when you multiply them, you just add, right? You just converted your multiplication math into additions, right? So therefore, right, multiplying these two factors together, right, here and here, right, just gives you e to the j times phi 1 plus e to the j times phi 2, but then you can factor out this j, right, because they're common in both terms. Okay? All right, division is even harder. You have to switch this to negative sign. Okay? Right? Because when you divide two exponentials, or two powers, right, e to the 3 times divided by e to the 5, right, that's actually e to the negative 5, right? It's 3 minus 5, right? Right? So all of these multiplication and division stuff that's used to be, right, that you're gonna you that used to be you have to use trig identities to figure out. Now you can just do it by adding and subtracting. Okay, there's one more little caveat, right? So this is actually not the real function you're dealing with. Okay. Okay. What happens is that once you do your calculation, what you need to do is you need to take the real part of the calculation in order to get the real voltages out. Okay? The imaginary part gives you a phase between them. Okay? So the real part actually gives you the amplitude, right? But then the imaginary part gives you the phase. Okay? So therefore, right, when you take the real part of e to the j times phi 1, it turns it into a cosine function, right? When you take the real part of this, it turns that into a cosine function. It goes back, okay? So when I do the real part of z1 over z2, right? Okay? I'm going to get r1 times divided by r2, okay? I'm going to have cosine of theta. Oops. Why did the book change from phi to theta? Theta 1, theta 2, right? Okay. So when you want the real part, right, you change the e to whatever, right, into the cosine, okay? Because by definition, right, the real part is the cosine of that same function, right, without the j. Everyone okay? All right. So let's play around with this a little bit, okay? So let's say you have some wave, cosine waves, right, that depends on space and time. Is this familiar to the general physics 2 students when we did waves? This is like what Hannah said it. What does this sound like? What type of waves is it?
Electromagnetic.
Electromagnetic wave, right? Yeah. Okay. In fact, this is voltage, but then you can just figure out the constant, and then you can actually convert this to, electric fields, right? Okay. And this wave has some amplitude a, right, cosine of kx minus omega t, right? So it's propagating in time and propagating in space at the same time. That sounds weird, but okay. Okay. So I can define this so that instead of dealing with these cosine functions, I can just take it to the x. Think about it in terms of like it's the real part of a imaginary exponential function. Okay. And now I can do easier math with it. I don't have to remember any trig functions, anything like that. I just need to know how to add and subtract. Okay? Because, right, this is subtraction between two inside, the stuff between these things inside here, right? So this is probably easier to write it like this. J k x minus omega t, right? If I want to separate these two from each other, right? This part goes in the new. This part comes out with a positive sign. This part comes out with a negative sign, right? E to the j kx multiplied by e to the minus j omega t, right? It's just the ratio between them two, right? So you can do all these math with it without having to, googling. Oh, what's kx? What's cosine of kx minus omega t? I don't remember what that is, right? Okay. Right? Just be a little careful, right? To get your real answer, you have to take the real part of it, right? Okay? Don't just plug in the imaginary part. Sorry, don't just use the complex numbers as it is as your result. Okay? The other thing you can do is you can take derivative easily, right? My favorite thing to take derivatives of is, is exponential, right? What's the derivative of e to the ax? Aex, right? Because everything else stays the same up here. You just pop whatever's the factor in front down, right? So same thing when you take a derivative, right? With respect to x, though, these are partial derivatives. So those of you who haven't have Calc 3, just think about them as just regular derivative where you ignore the t, okay? Okay. So when you take this derivative, right? So the j and the k is the constant in front of the x, right? So that pops out in front, right? The rest stays the same, okay? When you take a time derivative, right? Now we're ignoring the x part, right? Now the constant is actually j and the minus sign and an omega, right? And that's what pops down, right? Okay. One more little note that's very interesting, okay? Okay, what's cosine of pi over 2? Anyone know what that number is? This is something you still have to know, unfortunately, about cosines. It's cosine of 90 degrees.
0.
0, right? So I wrote 0 here. Why did I write 0 here? That's dumb, right? Right. J times sine of pi over 2. What's sine of pi over 2? Yeah, you get 1, right? So essentially, I just wrote J here, right? That's all I wrote, right? That's equal to J, right? Why did I write all this stuff? Because that's the same thing as e to the j pi over 2, right? These two are the same, right? And we're going to use this, okay? So, right, when you differentiate, let's say, this one, right? When you differentiate this electromagnetic wave with respect to time, right? Negative j omega pops down, right? That's like just like right there. I can just write, like it's as if this derivative just turns into this number here, right? Okay. Well, negative j, right? Well, actually, j is actually equal to this, right? Let me do this right. Shouldn't there be, yeah, there should be a j here also. Okay, sorry about that. I think I made the same mistake last time. These are so small though also, right? You see what I mean? There should have been a j here, right, in front of this exponential, okay? Well, this is nice, right? Multiplying exponential together is easy. You just add them together, right? Right? Since this is a positive number, I just stuck it to the end because it has the same factor of j in front of them, right? So when you differentiate, right, a electromagnetic wave with respect to time, you get the same thing, but right, with just a pi over 2 shifted, right, in the argument of the sine cosine function, right? These are called phase shifts, right? When you shift a sine cosine function, right, you're just adding this constant angle to it, right? Okay. Of course, there's still this negative omega thing, but that's gonna get absorbed in the amplitude. Okay. Okay. So let's play around a little bit. How much time I got? Got 15 to 20 minutes. Okay. So let's play around a little bit. So this is stuff that we did in general physics using sines and cosines, but I'm just going to do it with a complex notation instead. Okay. So let's say I have a alternate AC source, and the only thing that's in the circuit is a resistor, right? So since it's a resistor, it should obey Ohm's law. So I'm going to use lowercase v, right, equals to lowercase I times R. Okay. I'm going to make sure that I'm doing this the shortest way possible too by looking at my cheat sheet, so I'm not wasting time. Sure, from last year. Okay. All right. It's not super interesting, right? So for an AC source, right, we're just gonna define this as the voltage is equal to some constant voltage. Well, typically you will define it as cosine of omega t, right? Instead of cosine omega t, I'm going to define that as e to the j omega t, right? That's the same thing, right? Well, technically, I should put the real part, right? Okay. But a lot of times I would just kind of like drop it and not and just okay. If I have an imaginary number, I know that's not a real voltage. Only the real part is the real voltage, right? Okay. Right. So, right. So if I plug that over here, right, that means, right, the current here has to be whatever the voltage is divided by R, right? The voltage is already written up here, right? It's some amplitude of the voltage, right? E to the j omega t, right? And that's divided by R, okay? So one thing that's to notice is that this angular dependence here, right, is the same, right? Same, right, between them. There's no phase shift yet, okay? And I think those of you who took general physics recently is getting to where I'm like alluding to, okay? If I draw this, this is known as a phasor diagram. Anyone remember that? Yeah. So the current, right, this is the current as a function of time, right? And then if I draw the voltage as a function of time, they should line up with each other, right? Right? Because they are in phase with each other, kind of like a little clock going around. Well, the clock doesn't do that. So whatever my arm's doing, okay? Okay. Now, instead of in general physics 2, now I can actually tell you what these axes are. This is the imaginary side. This is the real part. Okay? Okay. All right, let's do something a little bit more interesting. Okay, a capacitor. Okay, so pretty simple. Okay. So once again, the voltage, right, is going to be the same thing. It depends on time. It has the magnitude. I'm going to write it as ej omega t once again. All right, I can define that. All right, so to figure out how does the current behave on a capacitor, right? The only equation I know about capacitor is that the charge on the capacitor is equal to the voltage on that capacitor times the capacitance. Okay? Of course, I can write the time-dependent version of this, right? Just lowercase everything. Okay? Right? I want to figure out the current, but I don't have current here. So what should I do? Current is equal to what? Right? The time derivative of charge over, well, time derivative of charge, right? How much charge is moving per second? That's current, right? Ooh, so that's going to be a little bit interesting, right? So if I integrate, oops, actually I need to do a little bit of algebra. I dt equals, okay, I'm going to explicitly write that this depends on time, right? And then dq on the other side, okay? I'm going to integrate both sides, right? Right? When I integrate the left-hand side, it's just this complicated function, okay? But when I integrate charge, right, I just end up with charge, right? Right? And charge is V times T, right? I'm just messing with algebra, right? So that means voltage times the capacitor is equal to the integral of the current dt. Okay? So how do I get rid of this stuff, right? I want to solve for current. It's inside integral. What should I do? Mm-hmm. Take the derivative, right, with respect to time. Okay. Okay. That basically knocks out the integral. Now I have some current as a function of time. There's a little caveat. There's probably a little constant of integration here, right? Right. But let's just set that to 0. Okay. Okay. So if I differentiate, this number, that's why I show you how to differentiate, right? That's going to be the same thing, but with this stuff, the constant falling off, right? Oops, let's just keep it up there. But this is going to be V naught j omega times e to the j omega t times another constant c. Okay. Okay. So notice that there's a j here, right? I'm just going to collect a lot of the stuff together. There's an omega here, there's a c here, there's a j here. And what is j equal to?
Square root of the
Mm-mm. J is equal to e to the j pi over 2. Remember this discussion up here? Right. It seems like I'm complicating things, right? But let's see what happens, right? If I finish writing this equation, right now I have two exponential I can just add. I mean, multiply together, right? Technically just adding. Okay, e to the j omega plus pi over 2. Okay? So now I go to my phasor diagram, right? Right, this is the imaginary part, this is the real part, right? What color did I make the voltage last time? Green? Okay. Oops, don't do that. Okay. Voltage as a function of time is going around like this, right? Going as the clock going around, right? How is the current compared to the voltage in terms of its phase? When t is equal to 0, if right, let's say voltage is here, right? Where should the current be?
to the left. Behind me.
Yeah, ahead or behind?
Ahead.
Ahead, right? Because if t is equal to 0, right, that means it's already at 90 degrees, right? Because pi over 2 is 90 degrees, right? So with this, right, I basically just derive this phase shift between resistor current, sorry, the phase shift between capacitor voltage versus its current, right? When we did this in general physics, right, we sort of did the same thing, but then I have to like look up a bunch of trig identities to do it, right? Right here, I just need to know how to add, okay? And adding is nice, okay? Right? Um, okay. Can I do another 3-4 minutes just to wrap up this impedance thing? Okay. Now that we have imaginary number, now I can actually show you what this thing is called, the impedance. Okay. Okay. So Ohm's law is nice, right? V equals, well, Ri, right? Whatever that is. Okay. So the complex numbers allow us to do the same thing with capacitors and inductor. Okay. These are known as linear devices. It's because the voltage, right, is always going to be some proportional to the current. Okay. But this proportionality is not necessarily just a real number, but it could be a complex number. Okay? Okay. So in that little previous example, we derived that, well, the current across a capacitor is this complicated thing, right? With a this j, I put back the j instead of the e to the j pi over 2, okay, just to mess with you guys. Okay. Right? This constant of proportionality, right? We can simplify that, right? Because we want to make it so that it looks like this, okay? Somehow the voltage, right, is going to be proportional to the current times some constant, okay? So in this case, right, the voltage, right, has to be equal to, what do I do? If I compare this equation and this equation, right? The difference between these two is this factor in front, right? You see that? oops, this factor in front, right? Okay, ooh, I'm not highlighting the right thing, right? So the factor in front is V naught in front of the voltage, but in front of the current is J C omega V naught. Everyone see that? Okay. Well, that means, right, I can substitute in to here, right, this whole thing, right? And that's what this turns into. Now I have something that's almost like Ohm's law, right? I have current, right, that's equal to J capacitance omega times voltage, right? If I divide both sides by J capacitor omega, right? In fact, I'm going to write it like this, J omega, right? Right? I have a law, a behavior. Let me just write it on the side here instead of this equation over here, okay? Right? These cancel out. I'm going to flip it so it looks like V equals IR, right? Is equal to some constant J omega C times currents I, right? 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 So this is for capacitors, right? For resistor, right? This is V times T equals R times I, right? Okay? So this thing in the middle here, right? For resistor, I'm going to generalize this to be impedance of a resistor, okay? Impedance of a resistor is just R, okay? But now we have this complex number. The impedance of a capacitor is 1 over J omega C, right? So now, in all the times, right, whenever I write Ohm's law for resistor, right, is ZR times R. What should be the Ohm's law for capacitor? Oops, not ZR times R, ZR times I. Let's do that with the lowercase. Sorry about that. These are meant to be lower cases, even though the V doesn't look like it. What should be in front of here? It has to be multiplied by current. ZC, right? Okay. So now all of these Ohm's law look the same, except you just have to put in the right constant in front. Okay. And by constant, I don't actually mean constant because this depends on omega. Okay. And that'll be a fun thing for us to play around in order to, filter in or filter out certain frequencies of things, which is what we're going to do in chapter 3. Okay. I'm going to leave it as an exercise for you to do the same thing to derive the inductor version of this. Okay. So instead of a integral, you're going to have to differentiate. So hopefully that's easier also. Okay. So that's all we have today. Okay.